Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. So this is the general recipe of the processing that we have done so far using MapReduce for processing graphs. And what we did actually is not just a special case; it's a typical pattern of how MapReduce deals with graphs. Typically, we perform computations at each node. We do some local processing, local computations, and then we pass this through the links, the outlinks. We propagate these computations through the outlinks, which indicates the traversal of the graph. And then in the reduce, we combine or aggregate some of these partial computations. So the general recipe, we present the graphs as adjacency lists, local computations in mapper, pass the partial results via the outlinks, the aggregation in the reducer, and we iterate until convergence. Okay? And this is controlled by external driver, by the way. We mentioned that earlier, and you will see it in the new assignment. When you have multiple jobs, MapReduce doesn't know that these jobs are related. Okay? So you have to control it through an external driver code that will do this looping and preparing the input and the output for each MapReduce job. And don't forget that we have to pass the graph structure between iterations so that we can smoothly loop over the iteration with the same input format. So that was the summary of what we did, and we are done with the first example, which was the shortest path, single source shortest path. Now we'll switch to another algorithm, which is very well known also, which is PageRank. Some of you are familiar with that. I think how many doesn't know at all about PageRank? Can you raise your hand, please? Okay. Can any of you know about PageRank?
I know of it. Yeah.
Okay. Good. Fine. Anyway, so what is PageRank? First, PageRank is used to give an indication of how pages over the web are important. Okay. So eventually, using this algorithm, each page or each node in the graph of the web will have a score. Actually, it is a probability. And that probability will indicate how important this page is, generally. Okay? How the algorithm works, we do what we call random walk over the web. So imagine that we started somewhere on a random page on the web, and we select randomly a link in that page, and we click on that link. When we click on that link, we go to another page, right? So it's like going between two nodes in the graph, and we keep doing that infinitely. Just imagine, okay? So this is called the random walk over the graph. When we do that infinitely, each node in the graph will be visited some number of times, right? If we do that infinitely, each page will be visited with some frequency. If we look at these frequencies indicate the page rank of the page. So if that page visited so many times in this infinite random walk, then it has a higher page rank. If it's visited very few times, then it has low page rank. Okay? So that's the mechanism of the algorithm. But the main idea is that if I have so many in links, then I will be visited so many times, right? But if also some of my in links are highly visited, I will also be visited a lot, even if they are few. And if my in links are few, but all of them are highly visited, highly important pages, then I will also be highly visited. And imagine that my web page My web page now is maybe linked from Google Scholar. Not very highly visited page. What if my page suddenly is linked from, I don't know, CNN? I made it to the news. Okay, so every CNN is now pointing to my page. There will be a lot of traffic, of course, because CNN has a lot of traffic. So lot of traffic also will come to my page, and that will raise my score. Even if it's just one link, but one link from an important page. Okay? So usually I say it that way. I am important if I know important people, or if important people are pointing to me. Okay, that's the idea of PageRank. Right. So mathematically, PageRank is a probability distribution over all pages. So if we compute PageRank for every page, then the total scores will be just 1 because it's just a probability distribution. Okay, so keep that in mind because this is an important note. As we said, it captures notion of page importance, and it was one of the key features that made Google to be that effective in web search. Now it is, of course, one of the features, but it was a very major feature in the web search technology. Now, mathematically, what is PageRank? This is how PageRank of a node is computed. One small detail that we didn't say yet. In the random walk that we described, we said that we will start from a page and we go randomly, right? Clicking on one of the links in that page, and then we repeat that infinitely. At some point also we can jump to any random page. So let's say that I got bored of that page, I can just write the URL of a new page and start from there. Okay? The model here has a probability of alpha of doing that. So there is a probability alpha that at some point I will go to a random page, not necessarily linked from the page that I'm visiting right now. And 1 minus alpha of the probability that I will visit one of the linked pages. Okay, so that's now the complete model. So alpha is called the teleportation probability. Okay. Type. Now, how PageRank is computed? Let's say that we want to compute the PageRank of page X. Okay. Page X is linked to from T1, from T2, from N pages, from T1 to Tn. Okay? We said that I am important if many important people are pointing to me, right? So my importance actually comes from the importance of those who are pointing to me. So it is intuitive that the PageRank of X will be a function of PageRank of the in-links. Okay, so as you see here, PageRank of X is a function of PageRank of Ti, where I is from 1 to n. This is n is the number of the in-links of X. Okay, but remember that every node that is pointing to me is not only pointing to me, right? It's pointing to others also. So I'm not getting the full PageRank of the node that is pointing to me. I'm just getting a fraction, because we said that if I am at a node, I will randomly select one of the links, one of the outlinks of that node, right? So what is the probability that I will be that link that will be selected? 1? No. 1 over the number of the outlinks. Okay? So that's why we will see that the PageRank of the node that is pointing to me is divided by the number of outlinks of that node. Okay? So for example, if we look at this graph, T1 has 3 outlinks, right? So it's like PageRank of T1 is distributed over the 3 links. 1/3 here, 1/3 here, and 1/3 here. T2 also has 3 links, so 1/3 here, 1/3 here, 1/3 here. Okay, and so on. So you will see that the contribution that is coming to X is related to how many outlinks of each of the neighbors, the inlinks to me. Okay, so it is the summation. Forget about alphas now. It is the summation of PageRank of the inlinks, but not the full. It's just divided by the number of links of that node. Okay, we'll see examples in the next pages, in the next slides. And that number now that is coming from my in links is multiplied by 1 minus alpha, because that's the probability of going through this model, right? And in the other side is the random side. Okay, I can go randomly by alpha, and the probability that I will be visited is just 1 over the total number of nodes in the graph. Okay, so that's the interpretation of the PageRank computation. So PageRank of a node has 2 sides, has a constant, which is alpha divided by n, so this is constant, plus contributions from my inlinks. So you can see here that it is a recursive computation, right? So PageRank of a node is a function of PageRank of other nodes. So when we have a recursive formula like that, one way of solving it is iterative, right? So we initialize the PageRank scores for all nodes, and then we go iteratively to compute the updates or the updated PageRank scores for all nodes. Now, of course, the effects at each iteration will be local, right? Each node, and if you look at here, in one iteration, each node will compute its new updated PageRank based on the inlinks, right? And their inlinks will be updated in the same iteration. So next iteration, the effect of this node, for example, will reach that node. So in each iteration, we reach the effect of my score will reach more hops. Okay? Very similar to what we discussed in the first part, right? So here's the sketch of the algorithm now. We'll start with seed PageRank values. What do you think should be the initial values of PageRank scores? Why is it 0? Because it usually will initialize by 0. If the initial value is 0, what will happen? The sum of them will be 0, right? But we said that the sum of PageRank scores should be 1, because that's a probability distribution. Okay? So typically we just initialize by 1 over n, so that the sum will be 1. N is the number of nodes in the graph. Okay? So that's the initial values. Each page then will distribute the credit to the pages that it links to, and then each target page will sum over these credits. Does that sound familiar? Similar to what we did in BFS. And we will iterate until values converge. We'll see examples right now. So we'll start to see how MapReduce will deal with that. We'll start with simple case. We'll just forget about the random jump factor, and we will not look at an issue called dangling nodes. We'll just ignore it for now, and then we'll come to it later. Here's a sample, here's an example, just to show you how the scores will be computed. So let's say that we have this graph. We have 5 nodes, so the initial value will be 1 over 5, which is 0.2. Now tell me how the scores, ignoring that we will jump randomly, there's no random jump, okay? So the first part of the equation is not there, just the second part. How we will update the scores. First, each node will have to distribute its PageRank score through the outlinks. Okay? So this node has a PageRank score of 0.2, right? How many outlinks from this node? 1, 2, 3. Okay? So 0.2 over 3 will go over each of these outlinks. So we will pass 0.06 over these 3 edges. Now, if you look at this one, how many outlinks from this one? Just 1. So it will just pass the same PageRank score through this edge. So that's 0.2. So 0.2 will go this way. And so on for each one. So this one has 2 outlinks, so it will distribute its current PageRank score through these two links equally. So 0.1 here and 0.1 here. Okay? So that's the first part. Now, after we distribute, we aggregate to update the score. Okay? So now, each node will sum the partial contributions, the contributions that is coming to it. So this node has 0.1 from here and 0.2 from here, so it will be 0.3. Okay, this node has 0.1 from here, 0.066 from here, so it will be 0.166, and so on. So this is the first iteration. So we have 2 parts, distribution of the partial scores, and then aggregating these partial scores. Where is MapReduce here? The first part is map, of course. This is similar to what we did in BFS. We distribute over the outlinks, and then we aggregate in the inlinks, in the reducer. Okay, and that's one iteration. Second iteration, the same thing. But remember, now the second iteration will start with the new scores. Okay, now we have updated scores. Exactly like when we started with new distances in BFS. Okay, so again, we will distribute the scores and then we aggregate them. Here is just a schematic diagram for MapReduce. So if we have these 5 nodes, then each node will distribute in the map, will distribute its score over the adjacency list, over the outlinks, and then this is what happens in shuffling. Now the colors here indicate different nodes. Okay. So this is N2, the blue, and this is pink N4. Okay, so we'll just group in shuffling. So now N4 will get this contribution and that contribution. It will add it in the reducer. Okay, is this clear? Any question about this? Okay. So this is one iteration. Okay, so we'll have to repeat that until convergence. So look at this and tell me where is the difference between this and what we did in BFS. So let's look at the map. Any changes in the map? Yeah, so that's the contribution. There was just the weight of the edge. Now it is the current PageRank score over the the number of outlinks, okay, and we emit it. We also emit the graph structure here, as we did in BFS. So that's the whole thing in map. It's very similar. How about reduce? What did we do in BFS in reduce? The minimum, right? What do we do here? We add all the contributions. So very similar. The pattern is very similar. Okay? Any question about this? So that means no questions, or there is a question? No questions. Okay. So that's just a comparison. So in map, we divide by n here, we add 1. Of course, when we relaxed it, we said we would add the weight. In the reduce, sum here, minimum here. Okay, now there are 2 more things that we need to consider. Of course, we'll repeat that multiple iterations, right? But if you remember the actual, if we go back to the actual computation, we have 2 parts. We are done with this. We did this, right? We did this, but we didn't do that. Right? Okay. Is it possible to do this?
Yes.
How?
This is a constant.
Constant, okay. So where should we add that? In the reducer, we should add this part, because alpha is fixed, n is fixed, so we can add this part, and also we can multiply this summation by 1 minus alpha, so we can do it. So that's easy, right? Right. So the first issue is done. The second issue is a bit problematic. What is the second issue? Let's say that in this graph, it is actually the reality that X has no outlinks. Okay, so X has no outlinks at all. What will happen? X will get contributions from its neighbors, but it will not distribute that to anyone. Okay? This is called dangling node. Dangling node means node that has no outlinks. It's just getting contributions from others, but it's not donating to anyone. Okay? It's greedy behavior. Why is that a problem? It will accumulate a score and will not distribute it. Okay? And if we do that, we'll find that eventually the sum will not be 1. The sum will not be 1. Okay? So we'll have to handle this. We will have to handle this. So this is the second issue of the dangling nodes. We'll have to handle the leakage of this part of the probability. Because there are things that are aggregated here, but it's not distributed. So how can we handle this? Any ideas? No ideas. So again, what is the problem? There is part of the probability distribution that is not distributed, right? Type. If we know this part, what would we do? And let's say that we know this. Let's say, مثلا, 0.1 out of the total 1 of the probability is leaked this way. If we know that, how would we fix the distribution? How would we fix the scores? So that means that the scores now if we sum them, we'll get what? If we sum the current scores. No, we'll not get 1.1, we'll get 0.9, right? 0.9. We'll get 0.9. Okay? Right. What should we do with this 0.1? We distribute it over all, right? So we can add to every node 0.1 over the number of nodes, and that will fix it. Now we'll fix the probability distribution again. What's remaining now is to know how much we leaked, right? Okay, we call this the mass of the probability distribution that was leaked. How can we get that number?
By adding summing the PageRank of all the pages.
Yes, so one way is to sum the PageRank scores of all pages, but that needs maybe another MapReduce job. Okay? And then divide and then distribute it maybe a third. So is there a way, an easy way to do it? Yes. The maximum probability that we can get is 1 over n. No, not 1. It's this value over n. What do you mean the maximum? Maximum what?
Yeah, any node in the graph eventually, if we don't have this done,
Yes?
the maximum n we can get is 1 over n.
No. Who said that? That's the initial value. That's the initial value. Initial values are all the same. But of course, pages will have different scores. The maximum is 1, of course, but that means that all of the others are zeros. It won't happen. Okay. But why do you think about the maximum?
If any node got greater than this is suspicious.
Where is this leaked part? Where? Where does it happen? In the dangling nodes, right? But can we detect these dangling nodes or not? They don't have outlinks. And we know them, right? When we handle them in the mapper, we know which node is dangling node, right? And we know its current PageRank score, right? Which is this part of the leaked probability. If we sum them all, then this is the value that we want, right? How can we sum them? Right, here's the solution. As you said, we can sum differently. Similarly, we can redistribute. We can compute these values. Okay. But we can do that in this. We don't need a second pass. Actually, we don't need a second pass. Here means another MapReduce job. But actually, we can do it without a separate MapReduce job. If we use counters, can we do that?
If you use counters, you will get you can get whatever you want to, but basically you will get it after the job.
We can get it after the map, and then we can access it from the reduce. Okay, so in the map, if the node is a dangling node, we add to the counter whatever value that node has now. With me, Kanaan? Huh? Okay. So we can do it in the map, sum all of them in one counter, and then use it in the reduce to distribute it over all nodes. Is it clear? Today, by the way. Okay. Counters are, you saw that in the assignment, right? You saw counters. You saw the number of input records and output records and all of that. That's type that is already defined for you. But you can also define your own counters, okay, in Hadoop. So if you do that, then you can define a counter that will keep track of this leaked probability. So whenever you find a dangling node in the map phase, you will add to that counter that portion. Okay? After the end of the map phase, then you will get that sum. Now in the reduce, you can now distribute that over all nodes.
And these are accessible to the job.
Yes. Yes. Okay? So that's how you can make it in single pass. You don't need a second pass. Is this clear? Is it clear? Really? Okay. Fine. When should we stop? When should we stop? Very similar to what we did earlier, right? We stop when the PageRank scores will not change. Of course, there are alternatives. We can fix the number of iterations if we want to, if we have a fixed time. Sometimes also we do, we stop not exactly when there is no change, but when the maximum change is very small. Okay? Because these are very small values anyway. So they might take some time to converge completely. So you don't have to wait until the complete convergence. You can just approximate it by looking at a very epsilon small maximum change that happened to indicate that you are almost done. Okay? Sometimes also depends on the application. You iterate and you stop not when the values don't change, but not when the ranking don't change. What do you mean by the ranking here? The relative ranking of pages. Okay? Yani if you care about the case when page A is better than or higher ranked than page B, not the exact score, then if the ranking didn't change, if the relative order of the pages based on page rank didn't change, you can stop. So that's another also alternative of a stopping criteria. Okay? Convergence for web graphs, we discussed that already when I told you that we cannot have a solid answer, but for PageRank, when they did it in the first time, I think it was, if I remember, 1998 or 1999, the algorithm. Of course, the web was much smaller than what we have now, but it took like 60 iterations. I don't know how many iterations we will need for the size of the current size of the web. Applications for PageRank, it's, as I said, it's used, of course, in web search as a fixed value that is added to the score of each page given a query. And it was a very valuable feature, of course, in web search. But it's not only about web search. PageRank is used in other applications. Some of these applications are here. Link recommendation or friend recommendation. You might compute PageRank scores for your community and then recommend those who have high PageRank. Identification of special nodes in a network. If you have a big network, big graph, you want to know the key influencers of this network. Okay, so you can compute PageRank for those. It's not only about web graphs. It can be used also as a feature in learning, in any learning applications. Trying to find Yeah, of course, in recommendations, yes. But I'm trying to tell you an application for which PageRank can be just a feature, one feature that can be used with other features. Other than recommendation applications. Trust or credibility of people. Yeah, but this is similar also to recommendation. But yeah, it's not. Yeah, trust also or credibility can be one application. Okay, any question about PageRank? So we covered now two applications, BFS and PageRank, and we saw similarities, of course, between these two, although they are inherently different, but the algorithms are very similar. Now let's talk generally about iterative algorithms. Of course, MapReduce is not efficient for iterative algorithms. One reason is that we have to write the output at the end of each iteration to disk and then read it back. Okay. And of course, each time you create or you start a new job, there's an overhead time. Okay, of reading the whole thing again. The issue of stragglers, I think we didn't talk about that before. What are stragglers in MapReduce? There are some tasks, and you might start to see that with larger data in more intensive jobs that you will run. You will see that sometimes you have, let's say, 10 mappers. 9 of them finished already, but one is very slow. It's taking a lot of time, and of course it's keeping the entire job slow because we have to finish the map phase before we start the reduce phase. This is called the straggler. Okay, and there are many reasons for that, many possible reasons for that. Maybe that straggler is getting more data to process, or more processing, it's doing more processing. Maybe it's slow. Maybe there are some failures that is happening at that node. Okay? All of that is now. Yes, but still this can happen, and that will slow down the job. Now it will be handled. By the way, sometimes with some failures, the job might fail. The fact that the framework is handling so many things for us doesn't mean that every job will be successful. If it happens, if a hardware failure happens in multiple nodes, the job might fail because we cannot do it. Okay, but here we are not talking about failures in particular. We're talking about the jobs or the tasks that take much longer time than others, and that will slow down the entire process. Now, if you think about iterative algorithm, that will be even more severe, okay, because we have so many iterations. If that happened in every iteration, then the entire job, entire pipeline will take much longer time. Also, the fact that we have to shuffle the graph in every iteration, this is, of course, very inefficient. And also we have to have a checkpoint at each iteration to see if we converged or not, right? So all of these things make MapReduce not very efficient for iterative algorithms. There are, of course, programming models that are designed to handle this. Lots of work. We'll talk about, inshallah, some of them later. But for today, let's think about how we can solve some of these problems. And this is the last part of the lecture. The first thing that we can do is to try to use a combiner. How can combiners benefit us here to make the jobs faster? Remember, what is the advantage of using combiners? Or when can we get really a good benefit from using the combiners? When? Yeah, that's the objective of it. But I'm asking, when can we really benefit from it?
You can preserve the state, right?
This is how. Okay, this is how. Not when can we benefit. What is the condition? So my question is, what are the conditions in the data that will allow us to get benefit from the combiners? That's my question.
Cheaper.
Yani if
Cheaper. Resource-wise. When you do the in-number combination.
okay, again, this is not the answer to my question. You are answering another question. So let me try to say it again. If we do in-mapper combining, okay, let's assume that we did in-mapper combining in every job. Is it guaranteed that it will really make a big difference?
There is a division.
If there is something to do, right? If there is something to combine, that's the key point. If there is something to combine, then combiners will be beneficial, right? Type. Now the question is, what is the condition by which we can get something to combine?
You have different values with the same key.
We have different output values from the mappers with the same key. Exactly. Okay? Type. Let's think together, when can that happen when we process graphs? With the two examples that we saw, what is the output of the mappers? Node and value, node and some distance or score and anything, right? Type. Now think, when can we combine? When we will have a chance to combine? In this case, each node. So let's draw it here. This node is emitting. I don't know what happens. Okay, is emitting intermediate output for its neighbors, right? So let's say that this is X, Y, Z. So there is an intermediate record for X, for Y, for Z. Okay? For that node. Now let's assume that the map task will process, of course, multiple nodes, right? So let's take another node. Another node will have adjacency list A, B, C. Now these two nodes will be processed at the same mapper or map task. So this will produce A, B, C. Is there anything that we can do here? The combiner will do anything? That's exactly what I wanted to say. Okay? The combiner will not do anything, even if I did the maximum. There's nothing to combine. Okay? You got my point now? How can we change the situation so that we can benefit from the combiner? Which means, how can we, to some extent, try to get things that we can combine together at the same mapper? So that's the idea of the optimization that we want to do. Think about the process here. Each node is emitting intermediate records keyed by its neighbors, right? Time. Let's talk about PageRank. That means that these nodes, if these nodes are neighbors, let's say that these nodes are actually neighbors, of the graph, then there is a higher chance to combine, right? Because neighbors of neighbors probably are common, right? So if that's the case, if in one mapper I will process nodes that are neighbors, or that are related, or that are linked, then there is a higher chance for the combiners to do something useful. That's the key idea. Okay? So if I partitioned the graph, okay, into components that are connected, and each component is processed at one node, then there is a higher chance for combiners to do some good work. Okay, so this is the idea. So in mapper combining will not benefit if there is no local aggregation that can be done. So that's just explaining the idea of in mapper combining. But we need actually partitioning. We need to partition. The default partitioning, of course, is just hash partitioning. It's completely random. And you know that the records that are read at each mapper is just determined by the splits. So whatever the records are written, the way that the records are written will be the splits that will be given to the mappers. Okay? We can control that, right? If we partitioned the nodes to put the nodes that are close to each other in one split or file, then we can get benefit of combiners. So we need to change the partitioning. Now this can happen differently in different domains. In social networks, for example, these are communities. But in web graph, how can we say that these are related to each other? It's not that easy. But we can have some heuristics. And for example, pages that have the same domain, probably they are linked to each other, right? And all pages under the domain qu.edu.qa. There are links, right? So maybe this can be a partition. Or at least they will be in the same file so that they can be processed by the same mapper. And if they are processed with the same mapper, there's a higher chance that they will emit intermediate output that have the common key. Is the idea clear here? Okay. Can you be with us, please? Can do this little.
Should I answer that? Sorry, really, I mean, I have an instance at work in SOC, so I'm just following up.
Okay. No. Try your best to be with us.
I mean, I wouldn't if it's not urgent.
Is that something urgent?
Yeah, it's an incident in progress.
Of course, partitioning is not easy because we need MapReduce jobs to do the partitioning if we do it. But as I said, there are cheap heuristics like the domains that we just mentioned. Okay, so we need to keep that in mind. That will make a difference. If you will be able to do some local aggregations using combiners, that will make a difference. Okay, remember that will be in every iteration. So it will make a difference eventually. Okay. The other issue that we want to think about is the issue of passing the graph in every iteration through between the mappers and reducers. This is a huge overhead. The graph is passed over the network. The complete graph is shuffled over the network every iteration. Now, how can we avoid something like this? The basic idea here is to separate these two things, separate the messages that we are passing from the graph itself. Okay, so let's for a second forget about the graph and assume that we will not emit any graph information from the mappers. We'll just emit the messages, whatever the partial computations that we are doing. Okay? Now we will need to get the graph information by the end of the job, right? So that we can start the next job. So we'll have to get it in the reducer in this case. But the question is how? Here is the idea. Let's say that we have divided the data that we have into two parts. Do you remember in database we do the join operation? Reem, can you be with me, please? When we have in a database two tables that have the same key, we can join them, right? So let's assume that here we have split our information into two parts. But these two parts are in the same order. When we merge them, it will be easy because we can just go sequentially over the two parts. We'll have the same key. Okay, so we can just join them easily. Okay, so imagine that this is the key, and that's also the key here, and they are in the same order. They are sorted in the same order. Okay, so to join them, it's just a matter of going sequentially over both together in parallel and just join them. So if that part was the messages that are produced in the map phase, and this part is the part of the graph structure for some specific nodes. If the order of nodes here is the same like the order of nodes here, then in the reduce phase we can just go through them in parallel sequentially and link them again. Did you get the basic idea or not? I think it will be
from the beginning, from the map to output on the map until the reduction.
okay. So in this case, we will forget about the graph structure from the map. The map will only emit the partial scores. So the map will not emit the adjacency list. So there will be no shuffling over the network at all. Okay? If we continue like that, then eventually we don't have the adjacency lists at all, right? We don't have the graph structure at all. That of course will not work, because we'll have to start with the graph the next iteration, right? So we have to in the reduce phase, in the reduce function, we have to link back part of the graph with the data that we are producing now. Okay? Let's assume that at one reducer, we got the information for specific nodes. Let's say, مثلا, nodes X, Y, and Z. 3 nodes only. So here we have the score for X, the final score for X, and the final score for Y, and the final score for Z. Let's say that we have only 3 nodes. And all of them were processed at the same reducer. Okay, so this is now one reducer. Okay? Now, if I assumed that the adjacency lists of X and Y and Z are also in the same order, but on HDFS. They are not in memory, they are on HDFS. They are in one file. But in that order, X, Y, Z. then I can easily merge them, right? I can process X coming while I'm reading one record from that file. And when I do that, I can merge this part with this part. And I can do the same with every record. Okay? So I am processing, I'm getting this through the mapper and shuffling to the reducer, and I'm getting this from HDFS.
So the reducer is reading from HDFS.
The reducer is?
Reading from HDFS.
Yes. Yes, the reducer can read from HDFS. But what is the condition here? What is the condition so that we can do this? Yes, the same order.
How?
By partitioning.
No, we don't know in advance the user which key will go.
But we control that, right? You did that in the assignment, right? Did you control that in the assignment? You directed all the words that start with the same character to the same reducer, right? So you control that. We can control that. Okay? So if we control the partitioning, okay, so that this nodes will be on that file as a graph, and also this node will go to the same reducer in that order. Command, yani it's we control the order, right? We can also change the sorting order to control the order. Okay? So that will be it. We don't need to shuffle the graph over the network. We can just read my part. Every reducer will read its own part reim from HDFS in the reducer. Okay? So that will be, let me,
Say again, just shuffling. Point of shuffling.
the what?
What do you mean by shuffling on
Sh-
your output?
yes, didn't we say that we will, in the mapper, we will not emit the adjacency list?
This is what you mean by
Yeah. And now, if I have, of course, multiple reducers, it's partitioned. Okay? The data, the graph is partitioned, and the partitioning that we use to partition the graph is exactly the same partitioning function that we will use in shuffling. Okay? So we did, it's like we did this synchronization manually. Okay, we did the partitioning, and with that partitioning, and with directing the messages of those nodes to this reducer, and this reducer will read from that file, then we can merge both sides of the data, the computations, the scores, and the graph structure. Let me show you this, by the way, this pattern is called Schimmy pattern. Okay, so it's reduced side because it's done at the reducer, parallel merge join between the graph structure and the messages. Why is it called merge join? Merge join is always between two parts that have the same key and they are sorted at the same way, so that we can just go one record in with one record there, okay, sequentially. This is called merge join. Parallel because it will be done in parallel over different reducers. Okay? And it's reduced side because, of course, we read from HDFS at the reduced time. But it's very important to have consistent partitioning between the input, which is the graph structure, and the intermediate data. Remember that we need two partitioning here, right? Partitioning of the graph, which is the partitioning of the input, because the graph is the input, right? The graph is the input to every job here, right? So we have to partition the input, and same partitioning has to be used with the intermediate output, intermediate data. Okay, because these are the two sides of the join. We are joining two things, right? We are joining the graph, and we are joining the messages from the intermediate output. So the mappers will emit only messages, and reducers will read graph structure directly from HDFS. Yes?
In the previous topic that we were talking about, we said we can partition the data in such a way that we send specific nodes to specific mappers.
Yes.
In that case, can't we just read the graph from the mappers rather than reading the reducers? So we design
Oh no, but we want to join after updating the scores, and we will not update the scores until we get.
Why do we need to just read the adjacency list from the HDFS and the mapper?
But the adjacency list already is available in the mapper, right? That's not the issue. The adjacency list of each node is already available. What we want to do is not to shuffle it over the network. So we should not emit it as an intermediate output. What we had so far is that the entire graph is shuffled because every node emits its adjacency list.
But now it's still emitting in the reducer, right?
Yes, but before we were emitting it in the mapper, which means that it will be shuffled over the network and from the reducer.
Yeah, but
So we saved the shuffling phase. We saved emitting the entire network over the entire graph over the network.
yeah, but my point
Did you get that?
Yeah, I get your point. I understand what you're saying. But if we can read of course we can read in the mapper, we can read from the HTML.
Yes.
Following the same method of partitioning the adjacency.
But why do you need to read it, You already have it in the
You
map.
don't need to emit it from the reducer then. You just emit the distance in the reducer, and you get the adjacency list directly from the HDFS in the mapper.
No, I didn't get that. Okay, so what do you want to do in the map?
In the mapper, we have the distance which would start from infinity, we said. The distance of each node. So it starts from infinity.
Yes.
And then we keep updating.
Yes.
We start only with this.
Okay.
But then we decide which node goes to which mapper. We said we can do this.
Which node go? Oh, okay, yes, partitioning.
Yes.
Yes, with the partition function.
Before
Huh?
the mapper phase. Partitioning before the mapper phase.
So you want to partition also the graph?
Yes.
Okay. Yes. You
Which
know.
we said we can do it.
Yes.
So in that case, since we know which node is going to which mapper, we can just read that partition of the adjacency list from the HDFS each time. So you don't even need to emit it from the reducer.
I got your point. But you already have it. You mean we don't need to have the adjacency list in the input. But what is the difference? What is the difference between reading it from HDFS and getting it as an input? It's the same thing. Both will be from HDFS.
Yes, exactly. But the problem is, in this case, you don't need to emit it in the reducer. You don't need to emit the adjacency list because you're reading.
No, we have to. We have to. Because we have the new scores.
But the adjacency list doesn't change, right?
The adjacency list doesn't change. Okay, I need to think about this. Okay. Yeah, we need to think about that. Okay. It seems like it's a bit complicated, so I need to.
You shouldn't ask this question. Now you feel
No, forget about Aman. Aman is not with us. No. Okay, so I think we just have a couple of slides. So this is showing you what's going on. Okay, so we have in the reducer we have the messages, and we have the graph from reading from HDFS. So we just merge them. Okay. Here's the modified reducer in this case. So in initialization, we open reading the file, we start reading the file. Okay. And in the reduce, of course, we might in case that it happens that you don't get any messages, okay, for a node, still the structure of that node is there. Okay, So you have to handle this. If what you are reading from the reduce input and what you are reading from the file are not aligned, then you have to output the one that has the graph structure. Okay, so you repeat until you align them, and then you what are we doing here? When n is equal m, that means that they are aligned. The node that is in the graph is the same as the node that is coming in the messages. So we will just update the values. Okay. So what is S here? What is S here?
S is an accumulator. It's just a local accumulator.
We are assuming here we are doing a PageRank. So we are just, summing. That should be initialized somewhere, I think. S, what is S? Should be initialized somewhere. Okay, so anyway, we add the values from the messages. Okay, so remember that we have two parts, right? We have the messages and we have the graph structure. So this is updating from the messages, and then we update the PageRank score, and then we emit both. We emit the node with the graph structure with the updated PageRank. So that's the merge. Do you see that? I know that you want to leave, but I want to make sure that you see it before you leave. Okay, so n, what is n? N is the vertex structure, the node. Okay, so we update n. N has the adjacency list. Okay, but it has also the PageRank field. So we update it. That's the kind of merging now. We update it and then we emit the node at the end. Okay. Why are here? Okay, so this loop, right? This loop, because we remember that we are doing two things, right? So let's say that we have aligning. Sometimes there are records here. Let's say that this is the graph from HDFS. There might be a record here with a key, but that key didn't get any messages here. We need to handle this. Okay, so if what I'm reading now is not like this, can you look at what I'm doing now? If this is X and this is Y, then we should emit Y until we get X here somewhere. Because Y didn't get any messages.
But it has the old. It has the.
No, we will not emit the structure, خلاص, the graph in the map.
We are. This is what we are doing. This is what I'm asking.
No, in the map we don't pass the adjacency lists anymore. Okay, so Y might not get any messages.
Okay, why we are limiting the structure?
Because to start the next job, no, that's what we want. We want to produce the graph again. But what we did here is to avoid shuffling it over the network.